Hello friends of .NET, I'm Imo Landworth and you can find me on Twitter at TerraJobst. I'm super excited about this event. I've rambled about this on Twitter I think almost a year ago when I said, how about I do a video series on how to build a compiler from scratch? And then I never did anything with that because as it turns out I was super busy doing other stuff. But thankfully you guys have all pinged me on a regular basis on Twitter and asked, what's going on there? I want to see this amazing talk of yours. So I finally had the time to put something together, and today is the first episode where we will start writing the compiler. Some of you have asked how long will it take to write the compiler. That's a good question. I don't quite know because my goal is to write this live, right? So today's episode will be 60 to 90 minutes. I will do a demo. So I should say I already have written the compiler. So one of the things I will do today is demo what the end result would look like, so you get an idea whether it's worth, keeping up with it or whether you want to do something else with your time. Before we go into the details, I have a few notes I want to go through to make sure we're all on the same page. So we will be writing the compiler from scratch. So there will be no magic compiler tools, no parser generators. It's just plain C#. The other thing is I don't require any computer science knowledge, even though I have a computer science degree. I think compilers are just, as any other software, if you know how to write it, it's just a lot of fun. We will be using .NET Core and Visual Studio Code. Both are free applications, so you should be able to download them and just follow along without any major requirements. And the cool thing is also both of them are cross-platform, so even if you're not on Windows, you should be able to keep up with the talk. One thing I should say, I'm not a compiler guy. So I work at Microsoft, I work on the .NET team, so I think of myself as being a decent developer, but I am definitely not a compiler expert. So if you're a compiler expert, you might be bored or highly amused. I don't know which camp you will fall into. I'd like to hear your feedback though, so if you're interested, keep watching. The one thing I would say is, so why do I do this course? So my primary motivation is to convince you that compilers are fun, because I've written a few compilers in my spare time, and I think those are cool things to do. And there's plenty of stuff that is actually very useful in whatever job you're doing, because turns out compilers are really mostly about how to handle trees, how to walk trees, how to do interesting stuff with trees. And trees are just a very interesting data structure that if you've never used them, you probably should, because they're really cool. So my goal is I will be streaming every Wednesday, 8 a.m. Pacific Standard Time, which will probably not work for the entirety of the world, but hopefully for enough people on the world so it makes sense to do it in a live fashion. It doesn't matter where you're watching, whether it's Twitch or Mixer or YouTube. I stream to all three of them at the same time. So just feel free to use the chat in there and ask questions. And if I don't forget, I will actually check the chat window every once in a while and try to answer your questions. The recordings of these episodes will go to YouTube. So even if you can't make the live slot, you will be able to follow later and find the stuff on YouTube as well, which is super useful. Of course, the source code that we're going to write is going to GitHub. My goal would be that at the end of every episode, I have one PR that adds all the code we wrote in that episode. Depending on how much time and how much energy I'm willing to spend after the episode, hopefully also get some notes. So even if you didn't follow the episode or if you're not a video person, you should still be able to catch up by just reading the notes. This brings me back to what's the goal for today. So today I want to start the project. We want to create the GitHub repo, get the initial code up and running, and then write the first part of it. So today what I would like to do is start with something simple like an expression evaluator where we handle priorities already, basic parsing of basic structures, and then maybe even print the parse tree so that we have some foundation that we can play with. All right, so without further ado, let's just jump into the coding portion of this. I mean, that's really the fun part, isn't it? So let me first say we need to pick a name, as any given project is. And I've played with plenty of names when I wrote the compiler. TerraJobst compiler, Imo's compiler, our compiler, and I never was really happy.
Have you ever considered Minsk?
Come again?
Have you ever considered Minsk?
I'm not entirely sold on the name Minsk yet. I think maybe we should pick maybe a better name.
Minsk.
All right, fair enough. Let's not upset the Klingon. Minsk it is. So let's call our compiler and our language for now Minsk, and then see where this leads us. So what I have here is the Visual Studio environment for the finished product. So I want to give you a quick demo on what that will look like so that you can decide whether you will run around. The annoying person that I am, I named it Visual Minsk because why not? So we have a small program here that we can load. And then you have an editor. Let me just maximize this and zoom in a little bit. So you have code colorization, which again is actually done by our compiler infrastructure. You can hover over identifiers and it tells you what it is. So it knows that guesses is a variable of type int. So we have type checking going. The language that I have, I was very uninspired. Basically what it does, it's just JavaScript or a little bit of C# maybe. I just wanted to have some language that is something we can actually play with. Like, I'm not a language designer, even though I'm on the C# language design team. I have my opinions on what I would like to see there, but for me it was mostly about writing the language. So I just picked something relatively easy to parse, and we can play with this probably as we're going as well. Let me open up the chat window so that when I'm going, I am actually able to see what's going on. Let me zoom out here. There's already plenty of questions. Yep. All right. So one thing, so what it does right now, I can actually run this program, and I wrote a little guessing game. So you can say, I would like to get hints, and then it will basically say, I guessed the number between 1 and 100, and now, what's your guess? And it basically does a normal binary search. So we can say 50, and then it says, oh, the number is actually higher. Maybe you want to get 75. Or the number is lower, and then eventually, hopefully, after a few guesses, you get to the actual number. So this is a very basic program here. We have functions in here. The functions take parameters. I have the ability to print to the console. We have string interpolation going. We have basic control structures like while loops and if statements, and you can assign variables, and what you would basically expect from a decent programming language. The IDE that we have here is actually, it doesn't have code completion yet, although that is something that I would like to add as well. But you do get live type checking, so if I make this in a float, you immediately get an error message that says this variable here we cannot convert float to an int because start game takes an int. Right? You also get some sort of symbol browser here where you can actually navigate between different parts of the language. So basically what you would expect, I guess, from anything that has the title IDE or something as basic as that. The other thing that I did, because this is actually compiled, so this is literally producing a .NET executable. So we can actually go to the folder here. If I remember where I put it, I think it's here, under samples. Yep, here's our exe, and we can actually open up this guy in ILSpy, which is actually kind of fun to do because you now look at the decompiled C# version of our language, which is kind of fun. So you can see, for example, that I use string interpolation here, but it just compiles down to a normal string concatenation, for example, right? Which I think I actually call string concat, I believe. Yep, that's what it does here. But you can see it in C#. Of course, you can't switch to our language because nothing knows about our language, right? That would be maybe even fun to do. Maybe somebody wants to do the decompiler for ILSpy for our language. That would be super sweet. But that's not what I'm focusing on. The other thing we can do is we can actually debug our code. So I can actually hit F5. And no, I did not write a debugger. All I did, I emit a PDB file that actually has debugging information in it. So that allows us to actually step through our code. So all I have to do here now is I can hit F11. And then Visual Studio will happily load our source file. I mean, it doesn't know anything about our language, right? So there's no syntax highlighting, no nothing. But I can actually do what you would normally do. You can do an F10. You can say, do I want to jump into the method ask for hints, or do I want to jump over that? I do an F10. So it asks for hints. I say no. And then for the run game, I can decide whether I want to run into that. I can do this. And as you can see here, is we even see the variables because they are actually part of the debug file. So Visual Studio knows what local variables exist. Of course, what you can't do, you cannot write expressions in here because, again, Visual Studio knows nothing about our language, so there's no expression evaluator or anything like that. But you are at least able to debug your code, right? So long you have Visual Studio installed. But you get the idea, right? Basically, we just emitted some IL and then added debug information to it, and that's all it took. All right, so that is what I want to demo about the actual finished product. Yeah, somebody's asking what language is the compiler written in. I will be using C#. Somebody asked for VB, but I don't know VB anymore. It's a long time. Yeah, somebody was asking what YAL stands for. Again, I'm uninspired. It's yet another language. So not really super curiously interesting. So I think, yeah, that's pretty much it what we have for questions right now. So all right, let's get started. So let's actually close Visual Studio for now. And let's actually start. So let's start by creating our bare bones folder. So we have a Minsk folder here. Let me populate this with some basic files here. So we have at least a git attributes, a git ignore, a git license. Let me do a git init. So we have an actual repository to work with. And then I think I want to create the repo on GitHub, make it public. Let's do this. Let's commit what we have. Initial commit. Yep, it helps if you add everything. And now let's just I keep forgetting. Yep, let's do that. Booyah. So we have at least the basics. Now let's actually open this folder in Visual Studio Code. Maybe the first thing we should actually add is a README file, just so we know what's going on. This repo is a compiler. Maybe we should also add, have you considered Minsk? Wharf, naming things. More details follow up, so we at least know what this thing will contain. Let's add this guy. Let's do this. All right, so now we at least have something to work with. So the first thing I will do is I will create our actual project. As I said, I'll be using .NET Core, so anybody can follow along on any operating system. So let's say I want to get a console app, and we want to call this MC for the Minsk compiler. And now let's actually open that guy again in code. All right, so here we are. All right, so now we have our basic compiler. I think I should be able to run this now. Maybe not yet. Yep, I want a .NET Core environment. Yes, please. I do not want to use the internal console because that never worked well for me, so I will use the external terminal. So if we now Control F5 this, I will hopefully launch this. Yep, it does that and immediately quits. All right, so this is our thing. So the first thing I will do, because it's much easier for us to work with, is not an actual compiler, but more like a REPL, right? Where we enter some expression and then immediately get some feedback on that. So let's do this. Let's say while true, and then we say var line, and we say just console.readline, and then we say if line, if string is null or empty. I guess null or white space is also fine. Line, then we just quit. Otherwise, we say if line equals 1 plus 2 times 3, then we say console write line 7. Actually, let me add a prompt here. Console right in this case. So we have something that we can actually see then what the output was and what the input was. Else console.writeLine error invalid expression. So let's see how this goes. 1 + 2 × 3 is 7. Wow. Did I say anything else? Invalid expression. Seems like we're already done. It's that easy, right? Yeah. Not quite. So let's actually do a little bit more. So the first thing I want to do is when we talk about a compiler, right? The first thing that a compiler does, if you just look at this source snippet here, is it will break this thing from characters into words. So if you think about the parser doesn't actually deal with individual characters. The parser deals with words, right? So you can think of the first part of the compiler as the Lexer, which creates words, and then there's the parser who creates sentences. And sentences are usually in tree form. So the very first thing I'm going to do is do that. And so in our case, because let's just start with the class Lexer, which basically will, actually, does this work here? Sort of. Lexer string text. Okay, we need a field. Oh God, no! Who wants that naming convention? Underscores for the win. I cannot stand this. So the first thing we need probably a position, right? So let's say private int position, and then we have, let's say, syntax token next token, let's say, right? So now the question is, what's the syntax token? Well, that is basically what represents a word in our language, right? So in our case, we would say, let's start simple and say we have, what do we need? What would be useful? I guess what would be useful is the position in the input file, and maybe the text, and maybe the kind. Like, is it a number or is it an operator, right? Like that sort of thing. Syntax kind. And then we just say our syntax kind is just an enum for now. We have nothing in it. And then let's just initialize properties for those guys so we can actually store them. All right, this should get us going. So the idea here is that this guy, like every time we call next token, we are at the current position in the file, and then we find the next word, take that, return that, and keep going. So in our case, so what we'll be looking for? So what we'll be looking for an expression evaluator are numbers, right? I guess. Plus, minus, times, divided, and of course, white space, right? Space. Let's just call this white space, right? These are the three kinds of words that, maybe parentheses would also be great, of what we can detect for now. So how about we start with numbers? So we say if char, actually before we do that, maybe what we should do is private char current, which basically gives us the current character. Let's start with something like, so if the position is basically outside the bounds of the text, then we return this guy here, which is basically the zero terminator. It's like conventional, I guess, for most systems to say if it's invalid, you return that guy. Otherwise, you return text position. So this gives us the current character. And then we probably want another method, private void next, which basically just does this. Like we just increment the position. So now we can say if char is letter or digit, is digit, current, then what we will do is we will remember where we are var start is position. We say while char is digit current. Next. And then we say, okay, length. I guess it's not really nice that we have this leaky abstraction here where we have a position and then kind of have to know what's going on, but let's deal with that for now. So we say length would be position minus start, and then we can say var text is text substring for start and length. So basically the idea here is that we will keep reading numbers, and then at the end we just create the word that represents the number. So we would say var, return new syntax token. No, not like that. So I cannot type this morning. What's going on here? Ah, I see what's going on. All right. So we get a new syntax token. We say the syntax kind would be, let's call this number token for now. And then we say the position is start, and then the text is text. Let's generate the enum member. All right, so now we have the number as text, which is probably for later phases not super useful. So normally what you do for tokens as well is you would say the Lexer is the party that is responsible for actually, reading it into the actual value. So let's do this. Let's just say int try parse on the text. And then we say out var value. And I don't really care right now whether it succeeds or not. Of course, we need to add error handling. But we'll do this later. So let me actually go here and let's actually object value. Let's accept this guy as well. So we have the actual representation. I'd use object for now because we probably have other shapes later that we want to have, like strings or floats. So typing this as int is probably not going to be a winning proposition. All right, then we can say, okay, var is whitespace, let's say, current, and then this guy basically repeats. We do something like that again, say, as long as this guy is whitespace, keep reading, and then we say whitespace token for now. And I think I just lost the light. Yeah, I may have run out of battery, so if later on it might get darker around my face. That might not be my mood, or depending on how the live stream goes, it might be my mood. We will see. All right, so now we have the white spaces covered, which gives us most of what we need. And then I think we only have the special cases now. If current equals, let's say, plus, then we do something much, much simpler. We would say position, let's just cheat here, C# for the win, position plus plus, text is this guy, and we don't have any value, and we call this the plus token. And then let's handle minus as well while we're at it. And then let's do, actually let's do them all while we're at it. Slash open paren, close paren, and then we call this guy the minus token. Let's call this the star token. This guy would be the slash token. This guy would be the open parenthesis token. If I get this ever right. I suck at typing, that's why IntelliSense is such an important thing for me. I just wish I had IntelliSense for English. All right, so now we have most of these guys, I think, and of course we screwed up the text here. Of course, I could use the original text from the input, but you know what? For these kind of tokens, it feels wasteful to do these substring operations because they all, fixed. And the nice thing with literables is that they're all intern, so you don't actually allocate new string objects for that. Quite handy. All right, so now the question is, if we get to this point, when we probably found something that we don't know what we should do with that. And so one thing that you can do is you can just say new syntax token, syntax kind, let's call this bad token. And yeah, I guess at this point we should have, I guess we can cheat again. Bad language semantics for the win. So we can say this would be text position -1 because this guy has already been incremented. So we go back. Yeah, I guess we need to do a substring here. Substring for the previous position, only one character, and then we have no value. I guess this is a comma, not a semicolon. All right, bad token we add to our list. All right, now we have our Lexer that can recognize numbers, plus, minus, slash, and whitespace. So before we go ahead, let's actually make our REPL just print it back to us. So we actually know what's going on. So let's actually allocate a Lexer, new Lexer for the line. And then we say while true, var token equals Lexer read get, well, how do we call it? Next token. All right. Next token. Oh yeah, one thing we should probably do that's also conventional is that there's this magic token called end of file. So at the very beginning, we should probably say if the position is text length or larger than that, then we just return the magic new syntax token, and we call this synkind end of file token. The position is the end of file. It has no text. Well, I guess we could cheat and say this is the magic thing here, and then we say has no value. So this is effectively done by pretty much any parser in the universe because that allows the reader to know when there's no more stuff coming. So this is basically a virtual token. It doesn't actually exist in the input file unless you think in C and you think the string is always zero terminated, in which case you can think of it as the zero terminator. All right, so now we have the token. Now let's print this guy. So let's say console write line. Oh, I guess we could say if token kind equals syntax kind end of file token, then we can just say stop it. Otherwise, oopsie, otherwise we write the token kind, and yeah, let's print the text as well, token text. In fact, let's also say if token value is not null, then console write yeah, let's do an interpolated string here as well. Let's say, what is that, token dot value, and then we can say console dot write line. So if you're thinking to yourself right now, this all looks horribly inefficient, that is kind of okay because we still write our compiler, right? So we want to not waste too much time doing stuff we don't care about yet. All right, so now let's see how bad I did. The moment of truth. So let's say 1 plus 2 times 3. That's not bad so far. So we have a number token, 1. We have a whitespace token. We have a plus token. We have a whitespace token. Funny enough, the whitespace tokens all have values, it seems. How did that happen? Oh, because I'm an idiot. Because there's really no reason to parse those guys. So now we need to say, let's say something similar like 123 minus 456. So now we have one token that is 1, 2, 3. We have a whitespace token, we have a minus token, we have another whitespace token, and we have a number token. And that's the end. So that's pretty good. So now we at least know the actual words, if you will, in the input. So that's pretty decent. But this is obviously not a parser yet. So let's take the next step here. So now we had a Lexer. Now let's do a parser. So the Lexer produces tokens, which you can think of the leaves in your tree. And then the parser produces the actual sentences, which are trees. And they're basically syntax nodes. So I'm fighting way too much with this. I don't know why the code folding doesn't work the way I want. All right, let's do a parser. So there's multiple ways you can do parser. Like if you read the most of the compiler books from the 70s or 80s, I'd say, they actually really highly optimize for streaming. So they try to not lex the entire input. They will usually like consume one token at a time and then maybe have a look ahead or whatever. But modern computers are really good. And so what I just will do is I will just say, screw this. I will just, actually, it's a parser. I will take the text here as well. And then what I will do as the first step is I will literally just run the Lexer on the entire input. So I will create a Lexer here, new Lexer, that I will give the text. This is one of those moments where I think I want a while a do loop. I will probably regret this choice because every single time I did that, I later on rewrote it into a while true loop. Token equals Lexer get next token. I'm bad at naming. Did I mention that? Yeah, next token. And then we say if token, let's say, is a syntax. Actually, no. That's the while part, right? While token kind is not syntax kind end of file. We keep doing this. Now what we need here is we need a list of tokens. So let's say var tokens equals new list syntax token. And then we will just say if token kind is not syntax kind whitespace, because we really don't care about whitespace for the most part, right? And if it's not a bad token, token kind, syntax kind, bad token, then we say tokens.add token. I probably need to use it for that guy. Yep. All right. Now let's say tokens equals tokens to array, because why not? And then we say create me if read-only field tokens. Sweet. Now similar to the other one, we need a position, which is basically our current token. Yeah, what's important is if you read this correctly, end of file is part of the token list, right? So that means I always know, even on an empty input, I will always have one token, which is end of file. So what we can do is we can say we have a private syntax token. Let's call this peak int offset. And I will later on tell you why I think this is useful. So we say index equals position plus offset. If index is outside the bounds, we will just return tokens length minus 1. We just return the last one. Otherwise, we return tokens index. So this means I don't have to think too hard when I want to peek ahead, if you will. And then we can say we have a private syntax token current, which basically just is peek 0. Basically give me what's at position. And everything else is just slightly ahead of that. So this is a nice thing when you Lex everything at once, because it means you can look ahead at the next token to make decisions on how you want to parse it, the entire input file, which tends to work pretty well. All right, now, so we have a class syntax token. Yep. What we also need is a syntax node, right? So let's do this. So let's say we have a class syntax node. Syntax node. And again, this guy needs an public abstract syntax kind. We will need this later to decide what kind this is. This guy will be abstract because it's basically just the base type for all my syntax nodes. And now let's think about how we want to represent the input. So this is some of these areas where maybe a picture would be more useful. So if you have an expression like this, right? If you say 1 + 2 × 3, what you really want is a tree representation, which roughly looks like this. So you have 1 here, you have the plus here, and then you, based on operator precedences, the tree will look probably like this, right? So in other words, you do, if you look at this from a tree structure, I'm actually really bad at drawing trees. Yeah, that's not horrible. And then this is 2, this is 3. So what you see here is basically a tree where the leaf node is effectively the tokens in the input file. And then you have a binary operator, plus in this case. And then, so if you want to evaluate this thing, you just basically say, well, plus, well, give me the left value, 1, give me the right value. Okay, that's another expression, 2 × 3, and then you add the result, right? So basically, in our case, this would be a node, probably a number node. This would be a binary operator node because it has 2 inputs. And everything else is just chained together, right? So if you do stuff like this, it will look a little even simpler. It will look like this, right? You would have two, right? Right, so like this is what would happen if you just parse this input here. So this is the kind of tree you want to produce. And we'll show later how this will work. So for now we need basically a number node which represents our leaves, and then our binary operators which are our interior nodes for that. So let's start with the fact that given that we will have expressions and statements later, let's just start with an expression syntax, which will for now just derive from syntax node and does nothing special, but it does simplify our design a little bit, I think. And then we have actual instances. So let's say we have a number syntax, which is of type expression syntax. And now we can say, let's have a constructor. Let's call this number syntax. So what does this guy need? Well, it only needs a syntax token, which represents the number. So that's the number token that we got. All right, now let's implement the abstract class. So in our case, we say this would be syntax kind number expression. Again, this doesn't exist right now, so we add it. And then we just store this guy as, not as a field. Let's make this a property. Okay, now let's do a sealed class binary expression syntax. In fact, let's call this number expression syntax just for consistency reasons. And then let's fix the typo. We have, what did I say, expression syntax, right? So what would this guy need? Well, it would get the left expression, right? So we have an expression syntax that represents the left side. We have a syntax token that represents the operator token, and then we have an expression syntax Right, and again, I suck at typing. Let me fix this. So let's store these guys. Property, and a property. Oh yeah, property explosion. All right, let's do this as well. And let's say this is syntax kind binary expression. So the only reason we have these kinds, by the way, is just so that we can just switch over them, which is slightly more efficient than doing an as cast all the time and have to check for the actual instance. It's basically, if you do F#, you probably think less of me right now because it's much easier in F# because they have union types. In C# you have to do this by hand. All right, so we have left, right. So that seems like we have our data structures at least somewhat in order for now. Now the part everybody has waited for, right? How do you parse this stuff? So let's start with a public method, public, and say we call this expression. Let's call this parse. So how do we do this? So logically, let's first think about how the tree structures work, right? So at the very bottom, we have numbers. So the first thing you want to parse logically is the leaves, and then you build the other structures on top of that, and then think of the method structure basically as mirroring the source structure, the tree structure. So what do I mean by this? Okay, let's start with the idea that first you parse a primary expression. Maybe it's easier if I just write it out. Parse primary expression. Then we can say while the current is syntax kind, let's call this plus token, or minus token. Oh yeah, there's one method that we really want to have, which is private syntax token next token, which basically says var current is current, and then you say position plus plus, and then you return current. So then we can say var operator token equals next token, and then we can say var let's call this right parse primary. Let's call this parse for now. Actually, is that how you want to do this? No. Parse primary. Never mind. Parse primary expression. And then we can say primary is now new binary operator expression, or binary expression, I guess, with, let's call this left, left operator token right, and then we say return left. Yes, and this needs to be kind. And then primary expression, in our case right now, is literally just we expect a number. So let's do this for now, and let's add another method called match syntax kind. So the idea is now if current kind is kind, then return next token. Otherwise, let's fabricate one. So I will explain later why this is super useful in the parser when you basically create tokens. But let's now say we manufacture a syntax token of the kind that was asked at current position. It has no text because it's manufactured, and it has no value. All right, what's going on here? Why does that not work? Oh, because this is the wrong type. Expression syntax, here we go. So we say var number token equals match syntax kind number token, and then we say return new number expression for the number token. All right, this should be what's happening here. Convert from syntax token to syntax node. Interesting. Did I mess that up? Yep, I did mess that up. That is a token, not a node. All right. So far so good. Now, the very first thing that you will probably find when you're parsing is you really want to see the parse tree, because if you mess that one up, that is usually very annoying. So I suggest we go to the syntax node and we add the notion of children, because once we have that, we can actually walk the tree in a generic way. So let's say we have an IEnumerable of syntax node, and we call this get children. And let's make this guy abstract. What helps right now, again, this is probably not what the production compiler will look like, but for now, let's just say syntax tokens are just nodes. Because if we do that, then we can basically pretend that syntax tokens are actually the leaves in our tree. So this means this guy does nothing. So we say return enumerable dot empty for syntax node. Yes, I need that. All right, now we can say our number expression syntax just returns our number token. Jesus, I'm really bad at typing today. I'm usually not that bad. Then our binary expression will first yield return our left, then our operator token, and then we say we want to return our right. So if you've never used yield, it's a very convenient way to write stateful iterators, where effectively this produces an enumerable where the first item is left. I could also just literally create an array here that would probably work as well, but I don't know. I find these a little bit easier because you can shuffle them around. And again, efficiency right now is not our primary goal. All right, now we can traverse the tree. So now let's actually change our main method here. Let's add a new method, static void prettyprint. And it takes, let's say, a syntax node. We probably want the indent, what we have written so far. Actually, we probably want this, right? We want to say indent. Indent starts with an empty string. And then we can literally just say console dot write, let's say node dot kind. And let's say this, if node is syntax token t, let's say console write no, actually let's just do this, and t value is not null, in which case we add the token value here. And then we just say indent plus equals, I don't know, what do we want? 4 spaces, 1, 2, 3, 4. I guess that works. And then we can say for each var child in node get children, we can say prettyprint the child with the indent That should do it for now. All right, now let's go back here. So instead of doing this, we say var parser, new parser for the line. And then we say expression equals parser.parse. And then let's literally just say var color equals console foreground, let's say, and then we say console dot foreground console, what is it, console color, dark gray. I don't know why I did this, but it seems cool. And then we can just restore the color here, I guess. No swap. Damn, I make me type everything here. And then we just say pretty print for our, what is that, expression that we just created. All right, so we have that part. Doop, 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 doop. All right, I'm inclined to run it now and see how bad I did. All right, let's do 1 + 2 + 3 for now. Oh yeah, we did really well. I guess we forgot our, yes, we should have done this, console dot right line. I guess that makes it slightly more that is interesting. Oh yeah, console dot write indent. It's cool when you construct the indent, but you also need to write it to the console. Otherwise, it doesn't do much. 1 + 2 + 3. Here we go. So we have a binary expression that is a binary expression that has a number expression with a number token, a plus token, and number expression. So that's effectively the tree that I drew earlier, right? The only thing that annoys me slightly is, what is that called? Unix tree. It would be nicer if you would get an output that looks more like this. So let's actually get these. Because we were looking at those guys a lot, so we might as well make it actually pretty. So we need this guy, and there's one more, right? There's the center guy that we need. Yeah, something like that. Now we have to think about how we construct these guys. How did that work again? I think I need something like is last. I think the default is false, I think. So how do we indent? We basically say if is last, then we say indent is plus this. I guess we could do this, right? If it is this, then it's that. Otherwise, if it is not the last one, then it would be that guy. And then how do we know something is to last? We say var last is node get children dot last. Let's just cheat here, and then we just say you are, let's call this last child, last child, something like that. And then I think I only need to yeah, where does this guy come from? Isn't that let me quickly run this. I'm not entirely sure. I might have messed up the what happened? Why did this disappear so fast? What is happening here? 1 plus 2 plus 3. That seems reasonable. Oh, we crashed. That is true. Last default to the rescue. All right. So this looks pretty ugly. So I think so what is happening here is, I believe that I think we create the indent too quickly, right? So boom. I think it's like this, right? So let's call this var marker. So we need to write the indent, and then we say write our marker, something like that, right? And then we say, by the way, this is indent one, two, three. I think I got that right. If not, almost. Yep, and it actually helps if your if check is not screwed up. Of course, we have to change this guy. Now I think we have something that is actually borderline readable, except it's not. Why is that again? I guess. It's like this, right? It's last, then it is 1, 2, 3, 4. Otherwise, it's man, this is like trial and error programming right here. Close-ish, except for the first one. Yeah, which I think the default is messed up. The default should be true, and then I think I have it. Man, pretty printing trees. The hardest problem in compiler construction, apparently. All right, so now we can actually read this thing. Not too shabby, I'd say. All right. So now in order for us to actually make something useful out of this, yeah, some people comment on my horrible string concatenation. But that's just the way it is for now. So now we have these guys here. Now I think the first thing I would like to do is deal with errors, because right now so far we have ignored any errors. We don't print anything, we just silently ignore them. And again, if you want to build a compiler, that's probably the first thing you want to pay attention to, because otherwise you will be lost forever in why stuff doesn't work the way you want it to, and it turns out that your parser just had a little heart attack in the middle and you never knew about it. So the first thing I want to do is I want to introduce the notion of errors, and I'm lazy right now, so I will just call them literally just a bunch of strings. So let's do this, and let's say we have a list of string which we call diagnostics, new list of string, and we will expose this to the public by saying public enumerable string diagnostics, and they just return our diagnostics, right? So now whenever we find something that is bad, like for example this, we can say diagnostics add, and we can say error bad token or bad character in input, which in our case we can probably say, let's do current here. Good enough. So this way we at least know what's going on. Of course, in the result we would record the position, but let's leave this for a later state. Now let's do the same thing in the parser. So the parser, where is it? Should have that as well. So private list string diagnostics, new list of string. So of course, at the beginning we should say diagnostics add range Lexer diagnostics, so we don't forget what the Lexer reported. And then every single time we see something bad here, like for example here, we can say diagnostics add error unexpected token. Let's do this, and let's call this what is that? Current kind. Expected. What did I say? Kind, I guess. All right, that's pretty decent. Now let's actually, if we find any errors, let's report them. So we can say if parser, I think we haven't exposed them in the parser yet, right? No, we have not. So let's say there's a public. What is happening with my tab key here? What is happening? I never had that. Public enumerable of string diagnostics, and we say this is you guys. All right. Tab to move focus. No, who wants that? Why would I ever do that? All right, so if the parser has any diagnostics, parser diagnostics any, then we say, you know, let's change this color to something dark red, maybe. I might regret dark red. It's probably unreadable. Well, we'll find out. for each var diagnostic in parser diagnostics console write line diagnostic. All right, let's check that out. So if we say, let's do a bunch of garbage. So we get back a parse tree, which I would like to highlight. So we get a valid parse tree back. It's just because we expected a number expression, right? So we got that one, and we have a bunch of errors. And then we get parser errors as well. So now when we say 1 plus, we get an error that says unexpected token end of file and expected a number token, right? Because it was after the plus. Unfortunately, we also have this situation where right now we are not reporting an error because what happened is we parsed an expression and then we didn't assert that when parsing was done, we're actually having end of file, which is a problem because now you can have basically trading garbage and you consider that legal, which is not what you want. So in order to address that, the cleanest way, I think, is for us to introduce a new type which represents the entire input, and we call this guy the syntax tree. And so the syntax tree will basically hold onto our expression syntax. We call this root, and let's say syntax token end of file token. Why would I ever want to do that? Make this a property. Make this guy a property. And then we can say also what we expect here is an enumerable of string, and we call this diagnostics. That's also the thing that we return. And yeah, for the time being, let's just do that, even though that is also bad, but good enough. We just store the enumerable as is. You know what? Not worth it. Let's do it the right way. Let's say we store this as an read-only list for now. And so we just say to array. So we don't have to worry about any craziness here. Then we let our parser, instead of returning an expression for the root, we return a syntax tree. Let's move this whole thing into another method. Let's call this method parse expression. Yeah, this way I should return an expression syntax still. Then we can say var expression equals parse expression. Then we can say match syntax kind end of file token, because that's what we really expect. Var end of file token. And then I can say return new syntax tree. Basically our diagnostics, the expression, and our end of file token. Now this is slightly cleaner, so instead of saying expression, we say syntax tree. Then we can say syntax tree root, and then we can say syntax tree diagnostics. We walk over these guys. Sweet. All right, so far so good. Now let's run this guy. Now when we say 1, 1, we get unexpected token number token, expected end of file token. So those things seem to work quite nicely, actually. Nice. All right, now let's think about priorities for a second. So if we do this, that is okay. Actually, no, before we do that, let's actually evaluate. Let's do that first. So how about we use this output now to actually compute a number, right? That's probably the I mean, we're not doing this just for the giggles here. We actually want to do something with the end result. So let's call this an evaluator, let's say. And let's say we give this guy, yeah, how do we do this? Jesus Christ. We give this, let's say, the root object, root. And then we have public int evaluate. And then we just say this is return evaluate expression. With our root. All right, how does this work? Well, we have basically, what kind of expressions do we have? We have a binary expression right now, and we have a number expression right now. Right? These are the only two things we have. So let's do this. Let's say if root is number expression n, then the result is the number token and the value. So now that is the problem, because we said earlier in the parser that we may not actually have a value, right? Because we didn't actually validate that. So let me actually go back to the Lexer really quick. Remember when we parsed this guy here, when we said, where is it? Here, when we said, oh, we don't know what's going on. Well, this is the moment where you want to make sure that you report an error. So you would say, if not, then we would report an error here that says diagnostics add the number cannot be represented by an int 32. Right, because we know it's only numbers for now, right? Right, we should just say isn't a valid int 32. Good enough. Because now we can say you can only call evaluate if you don't have any errors. Otherwise, it's illegal to call this method, which simplifies your error handling quite a bit. All right, now we can say if root is binary expression syntax b, well, we can say var left equals evaluate expression for b.left. We do the same thing for right. And then we say, well, if b.operator token kind equals syntax kind plus token, then we say return left plus right. Boom, boom, boom. Then we say this is else throw new exception unexpected binary operator. That would be B operator token kind, right? Because that shouldn't happen, right? So we have plus right, minus right. Star would be multiplication, and then this would be division. Let me say, what is it, slash token? Yeah. And then same thing here, we would say throw new unexpected note let's call this note. All right, so this one should give us something to work with. If we have any diagnostics, then we report them. Otherwise, we will for our syntax tree expression, no, root, I think it's called. Yeah. And then we say var result equals evaluate. And then we say console.writeLine result. Can I invert if? Super nice, because that makes it a little bit easier to read. Let's try what happens. 1 plus 2 is 3. 2 times 3. Well, actually, we don't parse that yet. Okay, 2 plus 3 minus 1 is 4. Seems right. And if we say a really large number, then we get it's not a valid int. All right, so this way we actually have some decent error handling and we actually evaluate stuff. Now let's actually go down to our parser and try to handle multiplication. Because how hard can it be, right? We already handle plus and minus. So all we have to do here are these guys, right? We would say, what is that, star token and then slash token, right? Now let's say 2 times 3 is 6. All right, that seems good. 6 divided by 2 is 3. Well, 1 plus 2 times 3 is not 9. So the reason this is saying 9 is because the parse tree does not actually honor our normal priority rules, right? Normally you would say 2 plus 3 binds stronger than this one here. But right now, because the way it's being parsed is we first parse 1 plus 2, and then we just say times 3. So we first evaluate 1 plus 2, which is 3, and then we say times 3, which is 9. But that's not the correct way to do the math. So we have to parse this differently. So the way we handle that is by just changing the way the parser is organized. So if you think about the parser for a second, right? So this is what's called a recursive descent parser, because basically what you do is you call these methods recursively, right? And so this is how you get the tree structure going. In my case, I'm not having really recursion right now because I just have a primitive while loop. So let's actually do a recursive part here. So the trick is you just split these guys into 2. And then this is what we would call parse multiplicative expression, let's say. I think the correct term for that is parse factor, which is basically to say, the things that are stronger together. Let me say parse factor is a primary expression times or divided by another primary expression. And then we say this is we call this parse term, I believe, is the usual term in the internet that they use, where we say this is a bunch of factors that are strung together, and then this guy only handles these guys. So let's see whether this actually solves our problem. Well, first it would help if it compiles. So we now say 1 plus 2 times 3. Now I get 7. And now I get a different parse tree, right? So now what ends up happening is we say 1 plus, and then the operand for plus is another expression, which is now our factor, effectively, that represents the result of the computation. So now we actually have the correct priorities in our evaluator. So let's do one more thing, because right now what annoys me a bit, yeah, I guess it doesn't matter. So we have that. Now the other thing that we want to do probably is support parenthesized expressions. So let me actually add another node for that. So what would that look like? So we have a sealed class parenthesized expression syntax, which is an expression syntax. There's no way I typed that correctly. Parenthesis, I guess looks good. Syntax token. So what do we have? Syntax token, we say open parenthesis token. Then we say we have the expression syntax, which is the expression. And then we have another syntax token, which is the close parenthesis token. And then I just store them in properties. We have to override a certain thing. So we say this is synkind what did we say? Parenthesized. You know what? I copy that. Put this guy here. Generate the enum member, and then we say, what do? We say yield return open parenthesis token, close parenthesis token, and then we say yield return expression in the middle. All right, so this is our thingy. Now we only have to parse it. So the way we would parse this is at the very, very bottom part, right? Where we right now say primary expression, we now have two kinds that we can expect. We can say if current kind equals send kind left, open parenthesis token, then I would say var left equals next token. Then I say var expression equals parse. This is one of those things where you want to have helper methods, so you don't have to understand the structure of your stuff. So what we would do is we would just have a private method, private expression syntax parse expression, and that just says return parse term. So you have sensible names, so you don't have to remember the structure. And then we can say this is parse expression, and then I can say var right is match for syntax kind close parenthesis token. And then we say we return a new parenthesis parenthesized expression, which is left expression and right. Is that all I needed? Let's find out. So now let's say we do 1 plus 2 times 3, right? And I think I crashed. So let's attach a debugger. Uh, 1 plus 2 times 3. Oh, I know what the problem is. I don't even have to look. It's this guy here. So we haven't handled our node in the evaluator. So if node is parenthesized expression syntax p, in that case it is just return evaluate expression for p dot expression, right? Because parenthesized expressions are just, you just evaluate the child of it. So now let's do this again. 1 plus 2 times 3. And it's 9, because yes, we first do this, which is 3, and then times 3. And so we have the proper node structure here. So what I also want to show here right now is if I say 1 plus 2, and I don't provide a closing parenthesis, we manufactured one here, right? So there's a close parenthesis token here that we added to the tree. So what's nice is that when you process your trees, you don't have to deal with null reference exceptions for parts of the tree that you just don't have, right? So the idea there is that You just have synthesized tokens for that, and you just rely on the fact that you have reported errors for those. And then this way, things tend to work much better. Now, the downside of inserting tokens is that you have to be careful how you structure the parser. Because when you insert tokens, you might end up in loop situations where you keep inserting tokens and you never terminate. So you have to be very careful that you write your parser in such a way you always consume tokens, so that eventually you will hit the end of file token and your parser terminates. Otherwise, you will create a lot of memory and nothing happens. All right, so this one, I think so far so good. The one thing I would like to add in our REPL, just for shits and giggles, is make the APIs a little bit nicer. So for example, we don't really want to deal with the Lexer and the parser anyway realistically, because what we operate on is the syntax tree, right? So what we can do is we can just have a method here, public static syntax tree parse, and we can just say give it text, and then we can just do var parser equals new parser for the text, and then we can say return parser dot parse, and that makes the APIs, I don't know, not a whole lot cooler, but I don't know, I like this one a lot more than having to deal with the parser. And it also reads slightly more logical. Syntax tree dot parse. You get back a syntax tree, right? Seems reasonable. Yeah, so the done thing I would like to add here is some pseudo commands. So we could say if line equals show tree. First of all, we say continue. More importantly, let's have a static here. Actually, it doesn't have to be static, not even. Bool show tree false, let's say. And then we can say show tree equals not show tree. And then we can say, I don't know, console dot write line show tree showing parse trees, otherwise not showing parse trees. So this way, when we run our thing, it looks a little bit cleaner. Oh yeah, it helps if we actually handle that thing too. Where's the pretty print here? If show tree, do that. Otherwise, don't do that. I guess we need to do that here now as well. We can say 1 plus 2. You get a result. I can say show tree. When I say 1 plus 2, I get the tree. So this way, we have some diagnostic information without without anything. And then I think the other one that I probably want, else if line equals CLS, we say console.clear. And then this way we can have it a little bit nicer as far as the console is concerned. All right, so I think we now have at least a REPL that kind of sort of works for us. Now let's quickly look at the project structure that we have so far, because right now everything is in one giant file, which I know some people prefer everything in one giant file. I'm not one of those people because it makes version control pretty ugly. First thing is, let's actually rename our namespace here into Minsk. Let me create a folder here which I will call code analysis. And yes, if you have ever used Roslyn, the Roslyn APIs, the ones that I just produced will look very familiar, let's just say. So let me just add a new file here, stuff.cs, and let me take everything we just built and put it into namespace minsk.code analysis and put the stuff in here. Now, of course, we need a ton of usings. And now I can just move these guys to separate files. So let's just go this one to this file. Move to type. Move type. Move type. Move type. Yes, do that. Actually, let me do a save all for now because I cannot deal with that many open windows. All right, let's keep doing move type. Move type. Move type. And now this is the last one, so let's just rename the file. All right. And then I guess here we can just hit the delete. Or we select everything again. That also works. Now we need to add a using for code analysis. And booyah. Now we have just our pretty print and the REPL in here, and everything else is neatly distributed in a bunch of smaller files. I'd say I'm at this point so far quite happy with the result. Now let me actually, because I haven't done this in a while, look over the questions that I've gotten. What do we have? All right. So most of the questions were related to what language are we using, which we already answered. Yeah, so some person asked, why do we duplicate the node information in enum and the class hierarchy? So right now what I have done here is I've cheated a lot, right? I've done a lot of instance checking. So if we look at the evaluator, for example, let me just quickly see where that guy is now here. We just do this, right? We basically just say, you know, if this instance is this instance here, and now with the new C# pattern matching, it's actually pretty concise. You can just do that. But for the most part, what you really want is you want a switch statement, because that is just much more efficient, especially when you walk larger trees. These things are much, much cheaper, because what you do is you basically ask the instance, give me an int, which is, you know, the enum value. And then the switch statement is just a jump table that directly dispatches to the block. And then you have, of course, the cast still occurring in that block, but you only have one cast, as opposed to you try this one, nope, you try this one, nope, you try this one, nope. So you do plenty of casts before you actually find the object. So instead of doing this, you just directly jump to the corresponding code block. For 3 or 4 instances like we have here, no point. But I wanted to set the pattern already so that we don't have to duplicate so much information later. Yep, somebody says we could do different node colors for the output. That's actually a good idea. We should probably do that. Any plan writing a new CLR? That will be a lot of work, writing a new CLR. A new language for the CLR might actually be something. In fact, that's what we do here, right? We compile down to IL, and that's basically new language. Blah, 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 blah. Yep, somebody mentioned LLVM. I've tried LLVM before. I have not succeeded yet in getting my backend up and running on LLVM, but it is something I would like to look into because my language, as you saw, doesn't really deal with object allocations, so it should be fairly straightforward to take the language subset that I have and emit actually native code for that. Might make the debugging a lot harder though. Yeah, so somebody suggests maybe we should have done commits for the individual items. That's a good idea. I generally do that, but when I get carried away, I'm not doing this. But generally, just how I work, I will commit logical chunks. And we can do this right now, actually, if we wanted to. Let me think about that for a second. Is that easy? Probably not right now, because you already have interdependencies everywhere. But I would say for our first episode, no, let's not do that. Let's do it the right way. To check out, let's call this episode 1. Yeah, I guess episode 1. Lexer and Parser, right? Just for good measure. And then we just say, add these guys. What we want to commit. I'm not sure I want to commit the VS Code ones, but yeah, it is what it is. All right, let's do. So here's all the stuff we're about to commit. Yeah, good enough. All right. Add Lexer and Parser. This adds the basics. Maybe we should say add expression evaluator. Evaluator. This adds the basics we need, specifically Lexer, Parser, and Diagnostics. That will lay the foundation for our compiler. I'd say good enough. So I think for our first episode, that is a pretty decent start. All right, so yeah, my lights are all fading, so I look very interesting, probably very dark. It's a very critical thing here. So I think the next episodes will focus a little bit more on getting more stuff from the language going, maybe some statements, and then also we have to think about how we want to run this guy. We'll probably start first with an interpreter, because it's much easier to do an interpreter than it is to emit IL, and then we will walk our way slowly up. All right, so we are pretty much in time. I was hoping for 90 minutes. We're now at 100 minutes. But, first things first. All right, hopefully you found this useful. If you did, please give it a thumbs up and share it on social media. And otherwise, I will see you next week. Bye-bye.